So we are now up here in Wilson Hall. So we're looking out on that pond. You probably see, if you look outside, you see this pond here, and then you see those lines, which are like those white poles over there. They are right on top. This one. Yeah, right on that one. And you see this blue arc over the pole over there. That's the meson lab, and that's this blue orange thing. That's it. So that's where we are currently. And then you see this weird kind of, I don't know, Sauron Lord of the Rings-like structure over there. That's our computing center. So everything starts here. That's where you will probably be going next week. The Cockcroft Walton that sits in this building over here. And there you've got a hydrogen body. Just like your standard fire extinguisher or so, the red and bottom things there. It has a lot of billions and billions and billions of hydrogen inside. And then you put that into a hostile environment. So we remove all the electrons from protons that are sitting on it. So the hydrogen atom is nothing but a proton with a circulating electron count. And you want the proton. So you remove the electrons, and then you accelerate the thing a bit, then you put on 2 more electrons, because we want just the proton, we put 2 more electrons. But it's easier to accelerate something with this, like clouded into 2 electrons. So you accelerate something that's negative through your Cockcroft Walton, you bring it to 750 kilo electron volt, 750,000 volts you put it through. And then in this tunnel, all this way out, you've got a linear accelerator. Nothing else but to say there are no bending things in the die, and everything just goes straightforward. And there you've got lots of cavities, and we'll see one example of those cavities over there. Like you see first this copper-colored thing over there. We can have a look. That's one of the accelerating structures, those cavities where you've got an electromagnetic wave going left and right, which pushes your particles through when they come in. That's one of those. And there, here you've got a lot of those, and at the end of this tunnel, this stuff is at, I think, a gigaelectron volt roughly, so 10 to the 9 billion electron volts. And then you put it into this booster accelerator, which makes it even faster, with 8 GeV. Then the protons are extracted, they are sent through a permanent magnet line to this recycler and main injector ring, where protons are accelerated even further to 120 gigaelectron volts, from 8 to 120. And then you start something which is called the antiproton accumulation process. So you might imagine that it's kind of difficult to produce antimatter, because it's just not there. Protons you get from a bottle. If you put antiprotons into a bottle, as the bottle is made of matter, it would kind of, well, produce a lot of photons and a lot of energy that is released in a very short time, and would probably today's Fermilab of the map. So you don't want to do that. So what you do is you take your protons, you accelerate them even further in here, and then you send them along a tunnel to the antiproton preparation ring. So what you do is you hit, in this building, you hit an ionium target with the protons. And when you fling these very high energy protons onto some metal, what happens is nothing else than if you fling 2 protons or 2 protons and antiproton onto each other, a lot of particles are being produced. You produce a lot of energy, and from this energy, again, a lot of hadrons. A lot of quarks come out, muons, ions, halons, what have you, all sorts of stuff, but also antiprotons, with an efficiency of probably about 1 in a million. So it's like playing lotto. But you do it very, very often. That's why you keep winning. So you play lotto very often. You get out of each proton that goes in here, you get 1/1,000,000th of an antiproton, or in other words, every millionth proton is 1 antiproton. And then you bundle those antiprotons and store them in this ring. You keep doing that, you keep hitting this poor metal there with protons, and you produce antiprotons, which you store here, accelerate again, and then inject into this guy, where they go clockwise around this. And you do that for about 24 hours or so. You bring out more and more antibodies, so it takes a while. And then you've collected about roughly 10 to 11 or so antiprotons, which is not really much in a cubic centimeter of some matter. You have 10 to 23 atoms. And so you produce about 10 to the minus 10 of cubic centimeter worth of antibodies. It's really nothing, but it's enough to bang them on protons. So you've got your antiproton circling this way, then you inject a final round of protons circling that way. You extract your antiprotons this way and send it into the peloton, where they then circle anticlockwise. Your protons go around this way, in the main injector, and then you inject them like this. So your protons will go around this way. You've got two sets of two beams, which actually you will hear about bunches. So they come in little packets of this length or so. And their size, so about this length, traveling around the ring, and their vertical extension, so their side view, if you look on top of the guy, they are about like 100 micrometer, 100 millionth of a meter in both directions. So it's a very slim arrow of particles that's coming through the ring. And these packets, these bunches, then collide. When you got those bunches, you don't have a whole beam, a whole like standing string of particles, because you've got those accelerating cavities, which go both ways. You push your particles, but at some point they have to come back these ways. And that's all the particles that arrive at the accelerating cavity when the accelerating cavity is just going back. They are down and they fall out of the beam. And that's why like all that stuff that is in phase with the accelerating cavities is being pushed on, it gets through the system, whereas the other guys just run. Okay, so you've got protons and antiprotons circulating in the thing, and then you steer them, so there's a hit, which is a difficult thing, especially when you start an accelerator the first time. You've got like 4.5 miles worth of beam, and you want to steer those 4.5 miles to a millionth of a meter precision, so that these two particles hit head on. It's difficult enough, and it takes usually a few months to be able to steer them that precisely. In the orange hall and the blue hall, and you have collisions in the detectors. And then we can actually have a look at that picture there. That's like one of the, that's an example event where you can see what is then happening. So you've got, it's actually the D0 detector, so the one that's in the blue hall. And you've got some, it's in yellow, you've got the tracking area, which is kind of your camera also, with lots of pixels. And whenever particles go through those pixels that you have in there, your camera chips, then they leave a little dot. And those dots you can connect with grids and find these lines. This green thing, for example, the muon that I told you, the stuff that just goes through a matter very easily, penetrates through all the tracking volume, where it's bent, and then it goes through the calorimeters, which are shown here, these white, red, and violet colors, and goes through the iron, which is used to return the magnetic field that you use to bend the particles in the track, and go through the neon chambers. Did I say this is D0, this is here? I'm sorry, so that's the one in the orange hole. And that goes through your neon chambers.